Welcome to the Explainer. I am absolutely thrilled you're here today. We are taking a deep, technical dive into Unit 3 of our problem-solving technique series. We're going to put on our algorithm designer hats and trace logical transformations step by step, exactly like a computer executing C code. So if you're ready to move past the basic definitions and truly trace algorithmic logic, you are in the perfect place. Let's get into it. Okay, let's dive into this and lay out our roadmap. First, we'll cover factoring methods traced. Second, array techniques in action. Third, we'll look at the power of partitioning. And finally, we'll wrap up with some practice exercises for you. Just to anchor us real quick, this is exactly where we are in the official syllabus. We are tackling Unit 3. We're officially moving past the introductory flowcharts and syntax from previous units and jumping straight into the deep, step-by-step execution of these specific techniques. All right, let's jump straight into part 1, factoring methods traced. Before we ever think about writing a line of C code, we really have to understand the underlying math. We're going to trace the exact numeric transformations for 5 classic algorithms. First up, finding the square root of a number, let's say 50, without using a built-in library function. We use Newton-Raphson iterative refinement. Basically, we start with a guess. 50 divided by 2 is 25. Then, we average our guess with 50 divided by that guess. So the average of 25 and 50 over 25 is 13.5. We repeat this. The average of 13.5 and 50 over 13.5 brings us to roughly 8601852. Another pass gets us to 7207085. By step 5, it converges beautifully to about 7071068. In C, this simply translates to a fixed for loop that continuously updates our guess variable. Next up, finding the smallest divisor of an integer. Let's test the number 91. We use the modulo operator to find the remainder. Let's trace it. 91 modulo 2 is 1, no match. We test 3, 4, 5, and 6, they all leave remainders, but 91 modulo 7 is exactly 0. Divisor found. A simple C for loop achieves this by just incrementing the divisor until the remainder equals 0. And hey, if that loop reaches the number itself without finding a divisor, you know the number's prime. Now for a classic, the greatest common divisor, or GCD, of 48 and 18. We're going to use Euclid's elegant reduction method. We take 48 modulo 18, which gives us a remainder of 12. We then shift our focus down to 18 and 12. 18 modulo 12 is 6. We shift again to 12 and 6. 12 modulo 6 is exactly 0. The moment we hit 0, our last non-zero remainder, which is 6, is our answer. In C, this uses a while loop and a temporary variable to seamlessly swap the values, which is exactly like the exchange pattern we already learned back in Unit 1. Now, what's really interesting about this next one is how prime factorization merely recycles our smallest divisor logic. To find the prime factors of 60, we literally just divide out the smallest divisor repeatedly inside a while loop. So 60 divided by 2 is 30. 30 divided by 2 is 15. Now 2 fails, so we step up and try 3. 15 divided by 3 is 5. 3 and 4 will fail for 5, so we divide by 5 to reach 1. Our prime factors are neatly extracted right there in sequence. 2, 2, 3, and 5. Our last factoring method is raising a number to a large power, like 3 to the power of 13. Think about a naive loop. It would multiply 3 by itself 13 separate times. But repeated squaring, also known as binary exponentiation, absolutely slashes this workload. By squaring the base and having the exponent step by step, we reach 1,594,323 in just 4 steps. This brilliantly illustrates how choosing the right algorithm directly improves performance as our inputs get larger. Moving right along to Section 2, Array Techniques in Action. For almost all of these next examples, we're going to use the exact same data set of 5 student marks, 42, 78, 55, 91, and 63. Keeping the data consistent lets us focus entirely on the shifting algorithmic logic. Let's reverse that array in place. We don't even need a second array. We just swap from the outside inward. First, swap the absolute ends, 42 and 63. The array is now 63, 78, 55, 91, 42. Next, swap the inner pair, 78 and 91. The middle element, 55, is left completely untouched. In C code, you'd write a while loop that simply increments a left index pointer and decrements a right index pointer until they meet in the middle. Keep this specific number in the back of your mind, 65.8. That is the exact average of our 5 array elements. We're going to use it as a benchmark for our next array technique. Let's count how many students scored above that class average. We run a linear scan from left to right. Is 42 greater than 65.8? No. Count stays at 0. 78 is greater, so our count becomes 1. 55? No. 91 is yes, pushing our count to 2. 63 is no, so we end up with 2 passing students. This logic pairs a C for loop to iterate over the array with an internal if statement to selectively increment our counter variable. Finding the maximum value works very similarly by keeping a running best so far. We initialize our max with the very first element, 42. Then we just scan. 78 is larger, so it becomes the new max. 55 is ignored. 91 is larger, so we update our max again. 63 is ignored. We arrive at 91. In C, this is just a for loop containing a continuous assignment whenever our if condition is met. Now, what if we have an array completely full of duplicate values? We can actually remove them in a single left-to-right pass. But, and this is a big but, only if the array is already sorted. Because the array is ordered, we are guaranteed that any duplicate copies sit right next to each other. We just iterate through comparing each element to the last unique value we saved. If it's different, we keep it. An array like 10, 10, 20, 20, 20, 30, 40, 40 shrinks down perfectly to just 10, 20, 30, and 40. Okay, now we reach the absolute star of the show, array partitioning. Let's partition our original array around the last element, the pivot, which is 63. We scan from the left. 42 is smaller than 63, so it conceptually swaps with itself to stay safely on the left side. 78 is not smaller. 55 is smaller, so we swap it with the 78. Now all elements smaller than 63 are grouped together. Finally, we swap to place the pivot itself right after the smaller elements. The array becomes 42, 55, 63, 91, 78. In C, this uses 2 pointers to gracefully shift smaller elements to the left boundary. Let's move on and see how this builds into an amazing shortcut. Let's try finding the kth smallest element, say the second smallest, which sits at index 1. In our previous step, our pivot 63 landed perfectly at index 2. Since our target index 1 is less than 2, we know for a fact the answer must be in the left subarray, 42, 55. We recursively partition just that left side. The new pivot, 55, lands exactly at index 1. Boom. We found our second smallest element, and we did it without ever having to fully sort the array. For our final array technique, we're leveling up to 2D matrix multiplication. We're multiplying two 2x2 matrices. Matrix A is 1, 2 over 3, 4. Matrix B is 5, 6 over 7, 8. The math requires us to multiply the rows of matrix A by the columns of matrix B. For example, to get that top left result of 19, we take 1 times 5 plus 2 times 7. To code this in C, we need a triple-nested loop to drive these row-by-column sums efficiently. All right, on to section 3, the power of partitioning. I want to pause here because this is huge. So the crucial point is emphasizing the single most critical structural concept you'll learn in this unit. It bridges everything we just did with what comes next. Partitioning isn't just a neat array trick. It is the literal engine that drives quicksort, which is the cornerstone of Unit 4. When we get to sorting, quicksort just takes the exact partition code we traced today and runs it recursively on both sides of the pivot. If you master the swapping logic of partitioning right now, you have already practically solved next semester's sorting algorithms. It's a real game changer. Finally, Section 4, practice exercises for you. We've covered a ton of ground today, tracing this logic step by step, just like a processor would. Now it's your turn to pick up the marker and apply this whiteboard logic yourself. I've got 3 actionable challenges for you. First, find the greatest common divisor of 36 and 24 using Euclid's elegant reduction method. Second, trace the step-by-step prime factorization of 84. And finally, partition the array 8, 3, 9, 1, 6 around the pivot 6, following the pointer logic we showed. And to wrap things up, here is a provocative question to leave you with. When you partition that array in exercise 3, exactly how many elements will actually need to swap positions before the pivot is finally placed? Grab some paper, trace it out, and I'll see you in the next explainer.